from the coffee break. It's time for the next session. Just a quick reminder about the OSGI t-shirts. If you haven't picked them up yet, it's time to do so. And the socks. Don't forget the socks. And the cake at 6 o'clock. So don't
6:30, actually. Dan said it's a bit later.
It's 6:30.
Yeah, it's like in the shoehorn between dinner and magic, so right in the middle there.
Okay. Okay. It's the next talk is going to be from BJ Hargrave from IBM and from the OSGI Alliance. He's the CTO of the OSGI Alliance. So you could really say he's one of the experts in OSGI. And now he's going to talk to us about promises.
Yes, sir.
Right. Please.
All right, thank you. Welcome, everyone. Today we're going to talk a little bit about promises and Java. So who here is familiar with promises? So you've used them in JavaScript? So, okay, who here is familiar with Java? I would certainly hope so. Okay, so today we're going to talk a bit about what promises are and the promises API that OSGI provides. And if we have a little time left at the end, we can talk about how it relates to Computable Future, which is part of Java 8 and on. So, what is a promise? Who knows what a promise is? What it really is? So a promise basically is an object that holds the eventual result of some task that might be synchronous, it might be asynchronous. But basically, so a promise can either be resolved, which means the task is completed and its result is known, or it can be unresolved, which means the task is incomplete, it's still operating. And so mostly if it's a synchronous operation, you'll always get a resolved promise back from some API call. But if it's a long-running asynchronous operation, it could be quite a while till the promise is resolved. So the unresolved promise doesn't have any results. At this point, it's just an object waiting. But a resolved promise has the result. Now that result can be either a successful completion, in which case you have a value that you were waiting for, or it could be an unsuccessful completion, which means that the promise holds the exception, indicating what went wrong. So this object nicely captures both the result or the failure of a task in one object. So when normally when you call a method that returns a promise, you will never get an exception back from that method. You will get back a promise with the failure inside the promise. So from the OSGI API, this is the high-level sort of object class diagram that we have in here. So the main part here is the promise. So promise is an interface. It has a set of methods on it, which allow the user of the promise to interact with it. But if you want to make a promise, you need to have something to resolve. And so the deferred class represents a thing that the task operator will use to resolve the promise, right? So a long-running task will create a deferred object. He will get its promise and return it. And then asynchronously, he'll be doing whatever that operation is, and then eventually he will complete the deferred by resolving it successfully with a value or resolving it unsuccessfully with an exception. And so what happens is when this finally gets resolved, the promise now calls callbacks. Right, so if you want to know what's going on in a promise, you call some API, you get a promise back from it. What you should do is register callbacks on it using a variety of the methods that the promise has. And then later on in the future, once your promise is resolved, you can get a number of different callbacks on your promise. And the other key class here, which is new in the 1.1 spec, is the promise factory. So basically, the nice thing about the promise factory is you use it to encapsulate all the executors you need to work with promises, right? Since there are potential asynchronous tasks, and the tasks might complete in the future, and your callbacks might run in the future, we need to know where are they going to run. And so with the promise factory is used to hold that information. So we look at the promise factory, we can create it with an executor or an executor in a scheduled executor service. And so, for example, if you were on a Jakarta E platform where you had to conform to the threading model, right, you can use the concurrency utilities to get your managed executor and then your managed scheduled executor and use that then to construct a promise factory, which is then suitable for use inside of your Jakarta EE application. And so you can, now that the promise factory is constructed with those parts, you can get them back if you need them individually, or you begin to use these other methods here. And so there's a nice convenience method here called submit. And so you can use submit to start an asynchronous task. So you just pass it the callable that you want, and it will asynchronously run that task on the executor. And when that task completes, either successfully with a result or throws an exception, that will be wrapped up in the promise that's returned by the submit method. And of course, the other thing you can do too is call deferred. And so then you can then return the promise that the deferred holds to your callers while you begin in whatever way you want to do your long-running action. And of course, sometimes you already know the answer. And so there's some nice convenience methods here that let you create already resolved promises, either successfully with some value or unsuccessfully with a failure. And so these are quite often convenient in using some of the other methods. If you want to do some recovery from exceptions that might be in the promise chain, you can use those methods to wrap up whatever value you might need. And also, we supply a default inline executor if you really want to keep everything constrained onto one thread. And so what this does is it steals the threads of callers to run the callbacks. Sometimes it's important in a particular operation, you just want to keep everything in line, and so we provide the inline executor. So in the API, we provide a deferred class I talked about before. And the point of the deferred is that it's an object that only should be possessed by the entity who's doing the work, the task, the asynchronous task. So you don't really give deferred out to other people. What you do is when you get a deferred, you get a promise from it, and that's what you return. And then while you're doing your work, eventually you'll call one of these two methods, resolve or fail, to resolve the deferred. It also is possible that while you're doing your work, you might get a promise from somebody else that holds the result that you then want to pass on to the person who's waiting for your results. So you can also use resolve with. So it's a nice way to compose promises in a completion chain. And of course, a toString, which is nice for debugging. So this is promise, but you can't quite see it because it's off the top. So this is basically the entire promise API. And if you've seen Computable Future, this is about a fifth of the size of that API. So the first thing is done. This is pretty simple. It just tells you whether the promise is resolved or not. There are methods to get value and failure, but typically you really don't want to use those because they're blocking. But sometimes if you do want to block on the promise completion, if you call on either of those two methods, it will block there until the promise completes, and then it will return you the value. Mostly, these are the important methods here, because you'll notice all of these return promise objects, which is very nice. And so there's a variety of things. There's simple callbacks. You can get called when it was resolved, or you can get called if it succeeds or fails. And then there's the remaining methods here are the nice things that compose promises together and begin to build what we call a chain of promises. So one promise begets another promise, and so on. And when the first promise resolves in the head of the chain, it begins to cascade down through the chain, running the operations that you've composed on it, and various callbacks, eventually getting to the end of the line, and it completes the final promise. So chaining, right? So this is the key thing here. Promises can be chained together. So this is the way you compose operations. And basically, most all of those methods we talked about that return promises can then be used to chain together with other promises. So an example here is that, well, that's the other thing is monads, right? Have you heard of the term monads, monadic programming, right? So all of these things basically return objects of promise. And so everything sort of wraps in on itself. And so it gives you a nice model of programming. And it also encapsulates, because the promise can hold the exceptions, you don't have to try catch blocks around all of these things you're calling. So if we look at a simple example here, so here's some fictitious API, which I need to download a file. I need to know the name of the file I download. So this returns me a promise of a string. So at some point in the future, I'll get that string back. And he might want to then find out, well, what is the URL for this string? And so he can flat map that onto another method called getMirror that returns a promise of URL. And so if there's an exception, it'll be cascaded. And the same thing again. Once I've got the URL of the mirror, I want to download the file. So there's another method here that returns a promise of the file, and we flat map that off of mirror. And so we begin to compose together these operations. Each of them has an individual function. Each returns a promise of its result, and we can simply chain them all together. But generally, when we do these sorts of chainings, we don't really need all of the intermediate promises, so we can simply sort of cascade them together into a single statement. And so it reads rather nicely. You can see that if I get the download name, I get the mirror, get the file, and then whoop, I get a promise of a file. Now, I can further chain onto it. If I want to take some action once the file is downloaded, I can then take that promise and, of course, chain another action on. Or if I really do need to block here, I can call get value or get failure on that promise and block while I'm waiting for it. So because promises nicely capture either the success or the failure of an action, they're very useful to build these sort of chains here. So it doesn't matter really that any of these guys throws an exception. I don't have to see it, it's nicely captured by the chain, right? So if the first guy throws an exception, the flat map isn't gonna do anything. He's just gonna cascade that exception to this promise, which then cascades the exception to this promise, and finally, the promise file holds the first exception that started the cascade chain. But see, one of the things that's really interesting with this model too is not only do you want to be able to sort of nicely capture the control flow of the success or failure of a sequence of calls, you want to be able to recover from those failures, right? Because sometimes things go bad, but you can recover from them. What if the URL download failed and you just want to have another retry? Maybe the second time will work. So we're going to talk a bit on using promises to recover from these failures. So who's familiar with B&D? Okay, so B&D is some tooling. It's an open source project. And in B&D, we build OSGI things with it. It's for bundle building tools. We get Maven plugins, Gradle plugins, Eclipse plugins. So it's some open source tooling. And of course, B&D also has support for a lot of the sort of popular repository types that people use, right? Maven, of course, is super popular. Maven Central. A lot of companies have Nexus repositories. Eclipse, of course, uses its own special flavor of repository called P2. And you can have other remote artifact repositories as well. OSGI has got its OBR repository format as well. So inside the B&D project, we've long had our own HTTP client class, right? So we've had this for a long time. B&D has had to run on a variety of different flavors of Java. So we can't, of course, use the new HTTP client in JDK 11 because we have to run on other versions of Java. And so we've used this, to minimize our dependency on third-party packages too, because we wanted to keep B&D as compact as possible, because a lot of people use it inside their other tools. There's quite a number of tools that use the B&D library sort of buried underneath there. Like I said, the Gradle plugins, the Maven plugins, all use it internally. And you'll find it actually is used in a lot of places. So we wanted to keep it small, so we have our own HTTP client class. But in the B&D build itself, we eat our own dog food. So every build of B&D in the CI system uses the previous version. So we're trying to keep up to date and keep testing our stuff. And so we were using P2 repositories in our build. Because we build Eclipse plugins, we needed access to Eclipse binaries to compile our source code against. And so we were using Eclipse's download site to get to these P2 repositories. But for a long while there, the Eclipse download sites were horribly unreliable. They just kept failing for a variety of reasons. And so I decided we had to do something about it. I had to improve the HTTP client class to recover from these failures, to try again. So the HTTP client already had some synchronous and asynchronous request methods. And fortunately, the asynchronous method already used a promise, so we were already eating that dog food. But I wanted to go take what we had and add retry support to it without too much swizzling of the code. So basically what I wanted to do is change the async method. We already had the return to promise and add retry support on it. So inspired by curl, I said, well, I want to specify how much is the recount and how much is the delay. I want to have an exponential backoff on the delay, so each retry we wait a little bit longer to give it more chance to get better. I wanted to recover from timeouts in case the connection trying to connect fails, or if the read fails partway through the read. If the server barks at me and gives me some silly 50x error, I don't want to handle that either. I want to have another try at it. So I wanted to handle all these kind of failures inside of our retry logic. And then, of course, because I was going to put all of this magic under the async method, I changed the sync method, of course, to build upon top of the async method. And so it uses the get method of promise to synchronously block. So it adds just some synchronous behavior onto async. And then, because I did all this stuff there and through this promise changing, I can add another layer on top of that. I added checksum validation. So if I was successful in the download, I would get the checksum value from the repository and compare it to the file I downloaded to make sure it wasn't corrupted in transit somehow. So both of these things I was able to easily add on to the existing code because we use promises already. So the key functions we have to do this sort of recovery are here, right? There's one called recover. So if it fails, it will give you the failed promise, and you can return a replacement result, which will then be used to resolve the promise in the chain. You can recover with another promise. So you might call a method that gives you a promise and direct it to recover with the value of that promise. And then there's the fallback too that says if the promise fails for any reason and this promise is successful, use its value instead. Otherwise, cascade it down. So there's a variety of different sort of recovery methods. Pick one that meets the particular needs you have. So let's take a look at some of the code in B&D that shows how we did that. Okay, can you see that? All right, so this is inside of the HTTP client, right? So you can see we have a send async method. So this is the main entry point in the HTTP client. After we've assembled our own HTTP request object, we call in the send async and to do some work. So the first thing we do here is we basically say, how many retries do we need? So right now we're only doing it for the get verb. We don't do retries on the other verbs. And what's the retry delay, defaulting to 1 second. And then we take that information and we call our private method, which does the actual work. So down here in this method, it takes the request that we want, how many retries remain, well, what's the delay for the next retry. We build up a connection object around the request, and then we use our nice submit thing. So then basically we submit the connection object to the promise factory. So this will take that connect object, which implements callable, and run it on the thread in our promise factory's executor, and immediately return to us a promise of the future result of that connection. And so then onto that, we do a timeout, right? So we say basically, if that doesn't complete within a certain amount of time, I want you to throw a timeout exception. And then we say recover with. So if either the original promise failed or the timeout failed, then we enter recovery mode. In this case, we use recover with. So we're going to return a promise which is going to be used to recover the original promise. So then down in here, we do all the magic work we need to do in recovery. We figure, well, what went wrong? What kind of went wrong was it? Was it a timeout exception? If it was, then we capture some stack trace. We cancel a connection in case it's still open. Log the failure. If we still have any retries left, right, then we actually go and do something. If we don't have any retries left, then we're just going to go ahead and fail it. And then finally we get down here at the bottom that says if we're going to retry, then we need to do a delay, right? So we take the existing failed promise, we tack a delay onto it, which is whatever our backoff is. So it might be a second or 2 or 3 or whatever it's escalated to. We compute what we want the next delay to be, so it'll be a little bit longer than the last delay, and then we turn around and we recall ourself again, right? So this is the method we're already in. So we effectively have some indirect recursion back to ourself, and that's why we use recover with, because send async returns a promise. And so this will sort of loop around, counting down the retries until we get to 0. And then if we get to 0, we just return a failed exception. Right, so this is a case where you know you want a promise because that's what your return of your method is, but you know that it's a resolved value already, and so we resolve it with this request exception. And so this enables us in this one method to do all of the details of the retry logic in the HTTP connection flow, where you can handle the timeout because we put it first, we can recover with it, and then by analyzing the particular kind of exception that we failed with, we can make different choices on how we want to recover. So what do you think of that? Pretty interesting, pretty neat. And there's no catch blocks in there at all. All right, that entire thing does not have a single try catch. So we let promises do all the magic for us in handling the exceptions and flowing them around and using the methods on promise to manage those exceptions through the recovery functions of the promise. So that was the first thing I did. It was basically build the basic parts for which to do the promise recovery loop. Now, of course, there are other things that we might want to, we need to figure out the kind of things we want to fail for, right? So, for example, one of them is the retry. So basically, I crafted a special retry exception internally, and we use that to tell the outer loop that this is a retry opportunity. Right, so for example, if the code returned by the server was one of the 500 series codes, then we say, fine, let's give it a retry if we still have a count left, otherwise he'll fail it for us. We also capture a set of these exceptions here too, right? So if it's a handshake exception, we'll throw a retry. If it's a timeout exception, we'll throw a retry. If it's an IO exception, we'll throw a retry. So we can classify which kind of exceptions that we want to retry by using a communication from the deep code in the logic by throwing a retry back out to the promise and letting the promise recovery logic either attempt another go at it or decide it's over, the retry count's exhausted, and then we'll throw a real exception back in or fail the original promise back with that failure. So that's one area we did the failure. And so the other thing that's interesting is checksum validation. Right, so this is another piece of code in B&D where we talk to Maven remote repositories, right? So this might be talking to Maven Central, for example, or your corporate Nexus thing. And so we have one method in here which we call fetch. And so fetch basically is going to go to the repository with so many retries and so long a delay. And so this similarly builds up a retry chain. So here is where we actually go and use the async method of HTTP, right? So basically, all that code we looked at before that returned a promise of the async operation, we're now calling it here. So this async method returns as a promise of type tag data, right, which is another type of the HTTP client. And so this represents the state of the async operation. So if we then chain it together with another promise that says this is a success. So if the promise was successful, then we flat map the successful promise onto another promise, and this promise is going to do our checksum validation. But of course, if we failed from the retry count earlier, we wouldn't even enter this block of code because this block is only called if the promise was successful. If it had failed, it would have completely bypassed this. And so in here, we're able to do all the fun stuff for Maven, right? We basically we build another request inside this request to go and find the SHA-1 file. And we flat map that onto an operation which reads the SHA-1, checks the digest, and check digest might throw an exception too. And so if he doesn't like it, he throws an invalid exception, which gets cascaded up into the promise retry loop. Because it's possible that the checksum might have failed due to some little glitch in the download, and if we have another try at it, we might get the correct file downloaded. And of course, it's also possible that there isn't a SHA-1 file, and we might need to fall back to the MD5 file, so we have that in there too. And then, of course, we have at the bottom the recover with loop that handles checksum failures, right? Because the first recover with loop was handling communications failures. This is handling checksum failures. And it's the same sort of thing again. We do recover with, and we use that, and we answer that by recovering with our own method call, which produces another promise. And so it loops around decrementing retries till we're done. And of course, the same sort of thing can be done for P2. Right? He has a similar sort of method, although P2 is a little different, because P2 actually puts the checksum value in the metadata, right? So when we get the P2 index file, it has in there the MD5 value. So similarly to before, we call the async method of the HTTP request, and if it's successful, we enter the success block, and this time we use then accept because it's a little bit different, but it's another method that takes a consumer instead of a promise. And then we basically, if it's all good, if it's not good, we can retry if the checksum fails. Otherwise, we can return null, indicating, of course, we're not going to recover because we're out of failures. So basically, it was fairly easy for me then, once I was able to, because we had used promises, the return type from the async method, to do all of this other stuff without affecting any other code in the rest of B&D. Right? All of this stuff was added, and no other part of B&D even had to know about it. All we had to do is go into the right places where a promise was, and we could chain onto it our recovery operation. So it makes for a very powerful model of adding these sorts of features without affecting other people, because you can chain and chain and chain and chain promises together. And if the promise is successful, the chain will flow over and ignore all the recovery methods. If the promise has failed, it will flow over and ignore all the success methods until it gets to a recovery method. And eventually, at the end of the day, this ends up in someone's hand who wants the value out of the promise, all right? And so he might be like the sync method, which basically just gets the promise. Where is he? He is... right, so the sync method is pretty simple, right? He basically calls the send async method, and then he blocks, waiting for the promise to complete. And so if the promise completed successfully, there's no failure, so we don't get a null, and we just return the value of the promise. If the promise had failed, then we just throw the exception back at the caller. And so from the caller's point of view, he just gets an exception. He doesn't even know there were promises under the covers doing all this magic and fun and exciting things for him. So that is an example of the sort of interesting stuff you can actually do with promises. So the neat thing is that you can get this and play with it today, right? So here's the Maven coordinates. This promise package is just a simple standalone package. It doesn't care about the rest of OSGI at all. You only have to use OSGI to use this. You can use this in any sort of job environment you want. So how much time do we have here? We've got a couple more minutes. Okay, so let's talk a bit about Computable Future. Who's used Computable Future? What did you think of the API of Computable Future? It's kind of big. So Computable Future was added in Java 8, expanded a bit more. They added actually some of the convenience methods that we already had in promises. They added in Java 8, the ability to create completed completable futures. But Computable Future was kind of a mess of an API, because it is a future and has all this other stuff on it, and every method basically has at least 3 flavors of it. So it's a very sort of large API. When you look at the Java doc, it's kind of scary looking. I was like, God, I have to learn 100 methods to know how to use this thing? And the method names are sort of odd too, right? In promises, we tried to use method names which look familiar to people. Map, flat map, the sort of things people know from regular streams in Java 8, or they might know from just general sort of monadic style programming. Another thing which I think is a big problem is that Completable Futures sort of smashes together the notion of using the Completable Future by callbacks and chaining, as well as resolving the Completable Future. So basically anybody who has this object can resolve it, not just the guy who's actually doing the asynchronous task. And so it sort of creates this bizarre error condition where people can resolve it themselves when it was really some other person's job to resolve it, which in promise we nicely kept them apart, because the deferred is the object that belongs to the resolver, and the promise is the object that belongs to the person who needs the result. And the other really odd thing is the Computable Futures are mutable, right? So in a promise is a one-way latch. Once it's resolved, that's it. It is permanently in that state from now until the end of time. It's either successful and has a value, or it's unsuccessful and has an exception. But Completable Futures have this ability to be re-resolved again through these obtrude methods. So you can take a resolved Completable Future and give it a new value or a new failure. So I'm not really sure how that really affects the cascading of the event call. So Completable Futures is a weird API. But if you're familiar with it, you can do, for the most part, a fairly one-to-one mapping between the methods on a promise and the methods on completion stage, which is sort of the main interface of Completable Future. So completion stage is probably closer to a promise in that it excludes the completion methods. But they have, the names are a bit unusual. And of course, there's 3 flavors of then apply, and 3 flavors of then compose, and 3 flavors of exceptionally. Basically, any method that might run a callback in the future lets you supply different executors to it and whatnot. And of course, the same sort of thing too. There's all these other methods on Completable Future, which are more like the methods we put on other objects, right? They have an ability to do an async operation, which we have with submit. Deferred, resolve, and fail, these are actually only new methods added in Java 9, so if you're still stuck in Java 8, you can't actually create an already completed completable future. And most all the other things have basically the ability to map them onto something else. We don't have a cancel operation because it's really the job of the deferred to decide whether he's going to complete or not. But there's, for the most part, I think there's at least a fairly good mapping. And so one of the things I actually started doing this week is on my system I'm adding 2 new methods to promise that let us bridge the completable future world and the promise world. So I want to add a method to a promise factory that takes a completion stage, and it will wrap a promise around a completion stage. And the other way around, there'll be a method on promise that will emit a completion stage. So you can turn a promise into a completion stage. So if you want to use promises, but you need to interact with other parts of the Java universe that are completable future people, this will let you, these 2 other methods will let you do that, add that on. So I'm looking to add that to the next release of promises. So that is my promise talk. Hopefully you learned something and you're excited and you'll go home and play with some promises. You promise? All right, thank you.
Thank you, BJ. Do you have any questions?
Yes. Okay, the reason we block and get failures is that's a very straightforward blocking method. So if the promise is failed, it returns you a throwable. If it's not failed, it returns you a null. Easy to deal with. If you call getValue, it would return you the value if it was successful, or it would throw an invocation target exception at you whose cause is the failure. So it's, you could write it that way, but then you'd have to have a try-catch block unless you really wanted to propagate this invocatable target exception back up. So this is probably more of an idiomatic way to do it. It's much simpler. You simply wait on the failure. It's either null or not, and then you take some action. It's a better control flow than, unless you really want to throw an invocation target exception at somebody. And if you want to do that, just call getValue. It does all that work for you. But if you don't want to do that, right, and see in this case here, I'm actually able to throw the real exception back at the person that I dug out of the promise.
More questions?
Tim.
Have you ever tried using so you have this kind of semi-recursive strategy with the failure? Have you ever tried doing the same sort of things with asynchronous processing of collections or consuming a list? Because you are able to, within the body of a flatpak, recursively run around until there are no more entries to the list to aggregate that value.
No, I haven't tried that, but it does sound interesting. I'm not sure if it would be worth the effort. I guess the question is, if when you do these sort of callbacks, you're context switching over threads and the executor to run these callbacks. So is the overhead of that worth it? I don't know. If you had I think if you had a large enough operation to do, then the recursion makes sense. But in this case, the example code I had here, or the actual code I have here, the recursion is only in the case of failure. So in the normal code path, you never flow through there, but you only flow through there to retry decrementing the count. So it'll only go so deep.
You were.
Actually, just wanted to add more information about the comparison between the computable future and the promises. Because one nasty thing about the computable future is that it is static methods without the executor, which wraps the promise factory actually. Just because the design of the promise factory, I think, is much better because you have this executor in there.
Right.
And with this static methods of the computable future, use internally this equals walk
Going pool, the common pool, yeah.
Java 8, which can lead to nasty deadlocks. So
right.
That's one of the negative points.
Right. So in that scenario, if you wanted to use that in a Jakarta EE world where you had to use managed executors, you'd have to keep using the overloads that take an executor and keep passing the managed executor into these calls to. Mhm.
can't really control that. So because it's default
Right.
and so with this, if everyone uses this promise vector, you have much more control how you think that this
Exactly. Yep.
I think there was one more question. Yep.
Well, the promise doesn't really have that in there. But the one thing that in this scenario I was able to do, right, is I was able to, if I'm in the retry, I can call cancel on the connection, right? Because I know I failed for some reason, even though the connection might be still trying. This method here will then take me in, and I can basically try and close the socket to force it. But the actual promise API itself doesn't have a cancel because the problem is if you've chained a whole series of promises together, by the time you get a promise, what does cancel mean? Well, what are you canceling, right? That's why if there was a cancel, it would be on the deferred. But of course, because that's the object that's held by the first guy that's doing real work. But then of course you don't have that object. He has his own object, and he's not going to cancel himself. So in this model, there really is no good place to put a cancel. You'd have to do it in some other means, sort of like how I did there, when I knew I was in a retry, I could try to cancel the last known connection before I went back and looped back up. Yeah, it's a sort of a best effort. Yeah, so in Java, you really can't kill a thread. It has to agree to commit suicide. Right, it throws an interrupt exception. Mm-hmm. Right, so that's sort of how the timeout operation works in promises, right? Because what happens is when you call timeout, we return a chained promise, and there's two guys racing to resolve him, right? There's a scheduled executor task that's going to execute when the timeout pops, and then the promise it's chained to. So one of them is going to get there first and win the race. And then, of course, the guy who shows up later, or if the timeout pops, then the other operation might keep running for a while, eventually attempt to resolve the promise, only to not be able to because it's already been resolved. But there's no way to really go back and tell the other guy to stop. It's hard. I mean, this is a general problem, I think, with any sort of reactive style of programming, right? Because the threads are unknown, you're all over the place. It is a challenge, right? I mean, I think you can, if you can put breakpoints, for example, inside the callback methods. If they're lambdas, you make them big enough so you can put a breakpoint on them. But it is a challenge. I mean, these sorts of programming models are much more challenging to debug, for sure. Well, every time, so basically when you call one of the methods, so let's say you call one of these methods here, you map or flat map, right? So you're going to pass it a function. So the question is, when is it going to run, right? If it's already resolved, it could run right now on this thread and give you back the new promise already resolved. But if it's going to run in the future, I need to know where to run it. And so when a promise is created, it's associated with a promise factory, and the promise factory holds an executor. So when the time comes in the future to run the callbacks, he can tell the executor to run them. And so that's where the executor comes into play. When all of these functions and predicates and things have to execute in the future, they execute on the promise factory's executor. Well, for example, the function of the map or the flat map, that will execute on an executor thread of the executor of the promise factory. So it's the promise factory who controls the threads that get used, not the callers of these methods.
I was wondering if calling enough of these methods would separate or make the executor,
Well, for any... Right, it's possible, right? So one of the things we've had, like when we use this in B&D, we were retrofitting our promise use into an older code base, and so we had a lot of blocking calls. And what happened was, is that if one of these callbacks blocks, you could jam up the executor. Right, so if you're writing new code and you never block in there, it works fine, right? It'll just queue up on the executor and work. So what we had to do in B&D is our executor is programmed with a synchronous blocking queue, and what happens is if there's not enough threads to run the work, it will throw a rejected callback, rejected executor exception back at you, and so we have a thing that just steals the current thread to do it. And that where we avoid that, but it depends on your needs, right? Normally, if you wrote good code, a regular executor will work fine. The fork join pull might work fine. But if you're trying to integrate with old code that does lots of blocking things, if you don't have enough threads in executor, you can jam up, and then you need to do the synchronous blocking queue so you can just run the rejected things right in line. And I think this man wants to kick me out. Oh, all right, thank you, everyone.
There's still 5 minutes to the next talk. So if you have
the next guy's going to set up.
No, okay, I'm not allowed to ask more questions. So thank you very much.